Hello, this is the student affiliates for the ACS. We're going to be performing some demos for you, and before much longer, I'm Declan. I'm the current president of SACS here at Kent. I am a BS chemistry major. I'm a senior. I chose Kent because I've got a wonderful glass powder department as well as a robust chemistry department, and I love both of those things.
Hi, my name is Madeline, and I am a fourth and final year BS/MS biochemistry student. My major is chemistry, concentration in biochemistry, and a minor in forensic sciences. And I chose Kent because I love bioanalytical chemistry research. So what we're going to do today is a demonstration called the non-burning towel. This is a towel, as you can see. And Declan here is going to dip it into what we call the mystery liquid. And normally I would ask the audience what this is, but since we're in a virtual setting, I'm going to let you know that it is a 50-50 mixture of, what do we have today, propanol and water. So propanol is a very small alcohol, but it is very volatile. And it is just mixed with your regular old tap water. I'm just going to kind of get out the excess liquid. Doesn't look like much has changed.
All right.
There we go. So you can see the towel is on fire, but it's not actually burning. None of the mass is being consumed by the fire. And the longer it burns, there is no change.
Yep, this image is fine.
Alright, go ahead and put it out. There we go.
Welcome to University Golden Flashes. My name is Kit. I'm a sophomore in chemistry with a concentration in biochemistry pre-pharmacy. I traveled the 28 hours here from Vietnam to pursuing the superior educational system and to one step closer to my dream.
Alright, so we have a diverse student body here, and there are a few of us here today that are going to perform a reaction of magnesium and dry ice.
Okay, for the material, we have a piece of dry ice, magnesium tonic, a molecule glider, a screwdriver, and then a handle for pen touch, and we also have PPI.
Yep, PPE is essential. Okay.
PPA, so.
Yep, PPE is essential when we're working with fire, which is what's going to happen here. So, first thing we're going to do, go ahead and pour the magnesium turnings into the dry ice. This is solid magnesium being poured into solid CO2. And then now we're going to light the torch and see what happens if the reaction works. Okay. Alright. It's just this one. Stand behind it.
Sure to not look directly out of this music.
Yep, do not look right on it. Try. It's getting there. There it goes.
It's amazing, right?
It's a very bright reaction.
Right. So the undergoing the rationale, the reaction is because magnesium is a lonely guy, so it's always he always wants to be married with
Oxygen in this
yeah,
case.
right. And then to be more stable, magnesium oxide, and then the reaction in here is the redox reaction between magnesium and oxygen. Sorry, magnesium and carbon dioxide. And where carbon dioxide come from?
I don't know.
Yeah, it's from the dry ice, which is the solid state of carbon dioxide. And then when the reaction undergoes, it's the exothermic reaction. So it's produce heat and then light.
Yep.
And what is left, Madeline?
Yeah, there are little black particles actually if we were to open it up. I'm not wearing the proper gloves, so I'm not going to. So Declan's going to step in. You'll see a bunch of little black pieces underneath the dry ice, which is solid clear carbon. So the redox reaction takes place and electrons are exchanged to leave elemental carbon behind.
Yes, Kent chapter, and we're going to be doing a demonstration of thermite. Kent here is going to be making the initial mixture. So first, he is going to start by mixing iron oxide, rust. It's not that scary, you see it everywhere, in with aluminum. And if you've ever dealt with any aluminum lawn furniture, it's pretty usual, pretty simple. But once he has mixed that together, rather than being the nice and friendly compounds that we know and love, they will have turned into a bomb, in fact. So, thermite reactions are a class of reaction that involve the stabilization of aluminum with a metal oxide. This releases an insane amount of energy, which is produced in the form of heat and light. Some common uses for it include underwater welding, and it's been used in movies before as special effects, although it's a little bit dangerous nowadays. But it's always been one of my favorite reactions. In fact, it was the first reaction that got me into chemistry, because I just saw all of the molten metal being created and spewed everywhere, and I thought, wow, I really want to do that. So the mixture of aluminum and iron oxide, while it has a lot of potential energy, it's not doing much. So right now, Kent is mixing sugar with a mystery compound, and that will help get it started. And at that point, it's simply waiting for a kick. He's going to be handing it to Andrea, who will be putting it into a fume hood, because this is very dangerous and we want to make sure that everything's safe. She'll be taking some concentrated sulfuric acid and adding just a little bit, and then it will be set off. And I hope you enjoy the reaction, because it's something to see. So thermite reactions are very difficult to look at because of how bright they are. So we're unable to see it directly, but you'll have a much better view thanks to the cameras. And that's basically thermite. And right now we're going to be doing the iodine clock. Andrea will be helping me for this reaction. So the iodine clock is a kind of timed reaction where based on the concentration of a material in starting products, it will determine the amount of time before the reaction finishes. So, as you can see, both of the cups, B and C, are both clear. B has vitamin C and an iodine mixture. Iodine, if some of you may know, is a dark brown liquid, but for reasons we'll explain later, the solution is now clear. C has a mixture of hydrogen peroxide, 3%, and liquid starch. You can get it in many different forms. So, if you could pour B into C, we will be starting a timer which showcases two competing reactions. If you could scroll that too. Yep. So there will be two competing reactions happening at the same time for this clock reaction. So first, hydrogen peroxide will cause the iodine, which is in the form of iodine ions, to be converted into elemental iodine, I2. And this iodine would form a complex with the starch in solution, and that would be dark blue. However, the vitamin C will consume any iodine that's formed and turn it back into the ions. That's why solution B was clear. It turned all of the iodine into a clear solution. Now, the vitamin C reaction is much, much faster. So, as you can see, there's not a single bit of coloring. But when the vitamin C is used up, it all turns blue. And if the water is warmer, it'll happen in a single snap. Now, there are different variations of this kind of reaction, which can be oscillating between clear and colored, and some versions of it can even turn orange, blue to clear, and then just cycle on as they still do reagents to. But this iteration is very simple and can be done for one cycle with minimal investment. And I think it's really awesome.
I'm Andrea. I'm working with Sachs. Today we will demonstrate an elephant toothpaste reaction. In this reaction, we are looking at the decomposition of hydrogen peroxide into water and oxygen. And hydrogen peroxide is typically stored in a brown bottle. This is because if hydrogen peroxide is exposed to light, it will break down, or it will decompose into the water and oxygen. So we have two different reactions set up. The first one is the iodide catalyst. Potassium iodide is the catalyst in the reaction, so it will speed up the decomposition of the hydrogen peroxide. And then the second reaction uses a yeast as an enzyme just to decompose the reaction. And we added food coloring and dish soap. The dish soap will capture the oxygen bubbles. And this is an exothermic reaction, so watch out when the foam. We'll have to see what will happen. Sorry.
So, as you can see, the potassium iodide started out a bit slower, but it generated a lot more foam, because I believe it did the reaction far more efficiently. The yeast alone, while it reacted faster, it did not generate quite as much foam. But it's a fun little experiment that you can do if you have access to 30% peroxide.